All right, in this video, we're going to continue our discussion of techniques for computing limits. And we're going to look specifically here at infinite limits and limits at infinity. So our objectives here are going to be to conceptually discuss end behavior and horizontal asymptotes. We're going to evaluate limits at infinity. We're going to find horizontal and vertical asymptotes of functions using information about limits. We're going to determine end behavior or transcendental functions and sketch their graphs. We're going to find slant asymptotes and sketch the graphs of rational functions. And we're going to solve applications involving limits used to find steady states. So those are all things that we're going to do in this video. The parent functions of y equals 1 over x and y equals 1 over x squared are going to be important here. So let's go ahead and refresh what they look like. Y equals 1 over x squared has horizontal asymptote at y equals 0, vertical asymptote at x equals 0, and it's in quadrants 1 and 2 here. Do my best to make it symmetric about the y-axis here. And it grows a little bit faster than y equals 1 over x because it's squared in the denominator. So we have points here like 1 over 1,000 and 10, and 1 million. And we have points like 1/2 and 4. And we have points like 1, 1, of course, and so on. So at x equals 1, y equals 1 over 1 squared. So 1 over 1 is 1 at x equals 0.001. Y equals 1 over 0.001 squared is 1 over 0.0000001. That's 1 times 10 to the negative third squared is 1 times 10 to the negative sixth. It's going to be 1 times 10 to the sixth, like that. At x equals 1/2, y equals 1 over 1/2 squared is equal to 1 over 1/4 is equal to 4. If you were uncertain about a limit to infinity, make a table. But if we wanted to let x go to some huge numbers here, like let's say at x equals 10, y equals 1 over 10 squared is 1 over 100 is equal to 0.00, I'm sorry, 0.01 at x equals a million. 1 over a million squared is going to be 1 times 10 to the negative 12th. And that's going to be really small. That's going to be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros and a 1. So we should be seeing that as x gets really big, y is getting really small, and is getting infinitesimally closer to 0. For y equals 1 over x, we have the reciprocal function here, and it goes in quadrants 1 and 3. And there's origin symmetry. It's an odd function. And we get points like negative 1,000th and negative 1,000. We get points like negative 1, negative 1. Get points like positive 1, positive 1. We get points like negative a million is going to be negative 1 millionth. So on. It's just reciprocals like that. So let's go ahead and just identify this at x equals negative 1. Y equals 1 over negative 1 is negative 1. At x equals negative 1,000th, y equals 1 over negative 1,000th is negative 1,000. And if x equals negative 1 million, y equals 1 over negative 1 million, it's going to be negative 1 millionth. Or it's thousands, 10,000s, 100,000s, millions, like that. All right, infinite limits. When we say infinite limits, we mean limits that go to positive or negative infinity, which are vertical asymptotes. The notation limit as x approaches a of f of x is equal to infinity means that the values of f of x can be made arbitrarily large as we please. So conceptually trending larger and larger, we're going to say that it's unbounded above or unbounded below by taking x sufficiently close to x equals a, but not equal to a, because there's the function is undefined at x equals a. The line x equals a is called a vertical asymptote of the curve y equals f of x. If at least one of the following is true, the limit as x approaches a of f of x equals plus or minus infinity, or the limit as x approaches a from the left of f of x equals plus or minus infinity, or the limit as x approaches a from the right equals plus or minus infinity, or any of those things, right? So it doesn't have to be all of those things. And it could go to different types of infinity from the left and the right, and then we would say that the limit just wouldn't exist. But in this case here, as we approach 3 from the left, we're getting a small number here in the denominator that's going to be negative. And so this is going to be a large negative number. It's increasing without, it's decreasing without bound. We subtract something from that, we're just getting an even more negative number. So that's going to go to negative infinity. As we approach 3 from the right, we put in 3 point something. We get a very small positive number down there. This is going to be unbounded above. It's going to go to positive infinity. Subtract a number from positive infinity. Doesn't really do anything because it's so large. Subtracting 4 doesn't do anything to it. That's going to go to positive infinity. This was negative infinity. This is positive infinity. So if you want to sketch it here to see what's going on, 1, 2, 3, 4 is your horizontal asymptote. And x equals 3 is your vertical asymptote. Like so. And if we want to think about where is this equal to 0, it's 3.5. Right over here, it's going to cross the x-axis. And we're going to approach 3 from the right. We go to positive infinity here. And this is a simple example. We're not going to cross the horizontal asymptote. We approach 3 from the left. We're going to go to negative infinity. The y-intercept here is going to be negative 2/3 minus 4 over 1 is negative 2 minus 12 over 3. It's negative 14 over 3 is negative 4 2/3. So right there. And there we go. It would look something like that. And you would be able to see here, we also could have done this with transformations, that if we had started off with 1 over x and then stretched it and shifted it to the right and then shifted it down, we would have gotten the same thing. So alternative problem statement, locate the vertical asymptote of f of x. How do you know it's a vertical asymptote? Because x equals 3 right there. When I approach 3 from the right, it goes to positive infinity. I could also say if I approach 3 from the left, I go to negative infinity. If I get either kind of infinity when I approach from the left or the right, it's a vertical asymptote. So let's move on here to problems 3 and 4. Let's look at tangent as I approach from the right. And we actually talked about this before. When we look at the graph here for tangent, here's pi over 2. And we come at the right, and we're going to go to negative infinity. And we come at it from the left, and we're going to go to positive infinity. Like so. And you can analyze this a little bit if you want to, that if you look at the unit circle here and you come up pi over 2 from numbers bigger than pi over 2, sine is going to be positive and cosine is negative. This is a positive over a negative is going to be a negative. We're going to have to go to a negative infinity. If you're coming at it from numbers slightly smaller than pi over 2, you're in quadrant 1. Sine and cosine are both positive, and a positive over a positive is a positive. You're going to go to positive infinity. But it's more than okay to go ahead and just look at this graph, like I said. And examine what happens as I come from the right and from the left. So now when we say limits at infinity, that's different than infinite limits. So these are going to usually be horizontal asymptotes, the things of what happens as x gets arbitrarily large or small, goes to positive or negative infinity. So let f be a function defined on a to infinity. Then find the limit of f of x as x approaches infinity that equals L. That would mean that the value of f of x can be made close to y equals L by taking x to be sufficiently large. We just get closer and closer and closer to that asymptote. And our end behavior is what we're talking about. So the line y equals L is called a horizontal asymptote of y equals f of x if either the limit of f of x as x approaches infinity is equal to L, or the limit of f of x as x approaches negative infinity is equal to L. You may get different asymptotes to the right and to the left, but if you have a horizontal asymptote on one side, you have to have a horizontal asymptote or no asymptote on the other side. You can't have like a horizontal asymptote on one side and an oblique or slant asymptote on the other side. That can't happen. Evaluate the following limits at infinity. So this is going to be limit as x approaches infinity of 2 over x minus 3 minus 4. And if we look at that graph, the end behavior of it, as we go towards the right, it's getting close to 0. And so this is going to be 0 minus 4 is a negative 4. If we look at this as it goes to negative infinity here, it also goes to 0, but from below, 0 minus 4 is also negative 4. So, and we had that graph up here already. Let's look at the end behavior of it again. We're looking at the ends here and here, getting closer and closer to y equals negative 4. In fact, I'm just going to write it that way because we already have the graph to look at, that this is going to be negative 4, and this is also going to be negative 4 using the graph. Now, if we look at the arctangent function, it's a special looking function here. And we talked about this one when we looked at our inverse trig functions. We said that it's going to approach one horizontal asymptote as I go to positive infinity, and another horizontal asymptote as I go to negative infinity, and I'm drawing this terribly. It's a little better. But out here, as I go to positive infinity, I'm tending towards pi over 2. As I go out to negative infinity, I'm tending towards negative pi over 2. This here, as I am taking the limit as x goes to negative infinity of 2 plus 10 over x squared, that's getting close to 2 plus 0 is 2. And we could actually draw that if we wanted to. 1, 2 here, and it would be up here and up here, and that from both negative infinity and positive infinity, I'm going towards y equals 2. So let's go ahead and look at some end behavior of polynomials here. Any even degree polynomial is going to resemble y equals x squared. And even if it is y equals negative x squared here, that we have limit as x goes to infinity of x squared is going to be a positive infinity. Limit as x goes to negative infinity of x squared is still going to be a positive infinity. Limit as x goes to infinity of a negative x squared is going to be a negative infinity. Limit as x goes to negative infinity of a negative x squared is going to be a negative infinity. So the ends do the same thing for any even power function or any polynomial whose greatest degree is even. So watch out whether the leading coefficient is even or odd. You need to know the highest degree, and you need to know whether the leading coefficient A is even or odd. If we have an odd degree polynomial, it's going to resemble y equals x cubed. And you're going to notice the ends are going to do opposite things. Limit as x approaches infinity of x cubed. The right-hand side of this graph is going to positive infinity. The limit as x approaches negative infinity of x cubed. Notice the left-hand side of this graph is going to negative infinity. If I have y equals negative x cubed, the limit as x goes to infinity of negative x cubed is going to be negative infinity. and the limit as x goes to negative infinity of a negative x cubed. That's this end behavior over here is going to go to a positive infinity. So these are basic examples to consider. If you forget the definition that's here in this theorem below, but limits at infinity of powers and polynomials. So let n be a positive integer and let p of x be a polynomial of degree n, where I have a sub n is the coefficient that goes with the x to the nth term, a to the n minus 1 is the coefficient that goes with x to the n minus 1, and so on, all the way down to a1 goes with the x to the first, and a0 is going to be the constant that goes with the x to the 0 term. An, the leading coefficient, cannot be 0 because then I wouldn't have an nth degree polynomial. I would have an n minus 1th degree polynomial. So I have to have a leading term there of the nth degree. Doesn't matter whether I'm going to positive or negative infinity. X to the n is equal to infinity. When n is equal to when n is even and an is greater than 0. This is going to be negative infinity. When n is even and a sub n less than 0. So always, all the time, it doesn't matter what the power is, even or odd, x to the n is going to be infinity. But if I'm going to negative infinity and n is odd, I'm going to be going to negative infinity. That's just what it is here. I'm just dealing with x to the n's there, not the entire polynomial. So let me get rid of that. So x to the n is going to be going to infinity here when n is even, and it'll be whatever the sign of the infinity is here when n is odd. 1 over x to the n is going to be limit of, and bring this exponent up here, that's going to go to 0 as I go to either type of infinity. We've seen those horizontal asymptotes. It doesn't matter whether n is even or odd. We have that horizontal asymptote at y equals 0. And then this is what I was talking about with the polynomial p of x. It depends on both the degree n and the leading coefficient, the sign of the leading coefficient. So we have what I was just saying, that if I am going towards, so n is even and odd, and an is positive or negative, and I'm taking the limit as I'm going to infinity here, or negative infinity. Positive and even is going to be positive. Positive and odd is going to be positive. As I'm going to infinity, limit as x goes to infinity of p of x. And then this is going to be negative. And this is going to be this is going to be positive. Anyways, we did that up there. Let me do it with pictures. We've got 4 pictures here. We've got n is even, a greater than 0. N is even, a less than 0. N is odd, a greater than 0. An. N is odd, an less than 0. So your behavior is going to be dependent on your degree and on your sign of your leading coefficient. All right. Let's do a quick example here. Limit as x goes to infinity of negative 4x to the 7th plus 9x minus 1. This is negative and odd. So negative and odd going to positive infinity here is this example. And we're going to go to, sorry, we said negative infinity. So it's going to go to a positive infinity here. This is going towards negative infinity. So left-hand end behavior of odd and negative, there we go, goes to positive infinity. Now let's consider f of x is equal to e to the x and g of x is equal to ln of x. Inverses of one another. Like so. This one goes through 0, 1. This one goes through 1, 0. Limit of e to the x as x goes to negative infinity is going to be 0. As I go to positive infinity here, that's going to be infinity. As I come at 0 from the right here, this is going to go to negative infinity. As I go to positive infinity over here, that goes to positive infinity. Can't go to negative infinity for ln. That does not exist because there's nothing over here on the negative side of the graph. So now think about y equals e to the negative x, which looks like this. And it also has interesting end behavior. Now as I go to positive infinity, I'm getting close to 0. As I go to negative infinity, it's going to go to positive infinity. As I get close to 0, I'm still going to get close to 1 there. So I have reflected over the y-axis when I put a negative in front of my x there. All right. Evaluate the following limits if possible. This does not exist because it's oscillating. This does not exist because it's oscillating. This is equal to 0, and that's equal to 0. But we can't evaluate these limits because they're oscillating behavior. We don't know what it's doing at the end because the end is just going back and forth between negative 1 and 1. Right? So we just talked about this. Sine and cosine both oscillate. So if we try and talk about the end behavior of a sinusoidal function like that, we can't. It doesn't have end behavior to talk about. Same thing for cosine. So don't get fooled by those. For tangent, let's look at that, and we're going to see the same thing, that we can't tell you what happens at positive or negative infinity. This is the pattern of oscillation that keeps happening. And so the limit as x approaches plus or minus infinity of tan x also does not exist, because we're not going to a finite number L. We're oscillating. So these limits do not exist due to the oscillatory behavior of trig functions. Let's talk about end behavior of rational functions here. And we're typically talking about horizontal asymptotes or slant asymptotes, also sometimes called oblique asymptotes. So if the degree of the numerator is less than the degree of the denominator, we're going to have a horizontal asymptote at y equals 0. So that means that the limit as x approaches infinity of f of x, we're calling it f of x, yes, it's going to be equal to, well, it's right there. Whether I go to plus or minus infinity, the limit's going to go to 0. Y equals 0 is the horizontal asymptote. So if I have degree at the top equals degree at the bottom, I'm going to have a m over bn if m is the degree of the numerator and n is the degree of the denominator. Have the leading coefficients, we're going to take the ratio of them. That's going to be the horizontal asymptote both to the left and the right. If the degree of the numerator is greater than the degree of the denominator, and I go to plus or minus infinity, we're going to have to use long division here. There's no horizontal asymptote, but we approach an oblique asymptote or a slant asymptote that we can find using long division. So degree of the top is smaller than the degree of the bottom. We can actually just say that that's 0. But let's actually go ahead and use a technique here where we want to make the negative powers here go to 0, and we want to get rid of the highest power in the denominator. It's typically what we want to do. So let's multiply this by 1 over x squared and 1 over x squared. So this is going to be limit as x goes to infinity of 1 over x plus 1 over x squared over 1 minus 2 over x. Any x's that are in the denominator terms here, as x goes to infinity or negative infinity, is going to go to 0, like so. This is 0 over 1 is 0, which is exactly what we expected from our rules up above. Degree of the top and degree of the bottom are the same. Let's multiply by 1 over x cubed. 1 over x cubed, limit as x goes to negative infinity, 1 plus 2x to the negative second plus x to the negative third over 1 minus 3x to the negative third. Any of these negative exponents as I go to plus or minus infinity are going to go to 0. This is 1 plus 0 plus 0 over 1 minus 0. So 1 over 1 is 1. Now degree of the top is greater than degree of the bottom. We're going to have to use long division, or you can split it up and let's just multiply everything by 1 over x and 1 over x. the f of x is equal to 2x plus 6 minus 2 over x over 1 plus 1 over x. The limit of this as x goes to infinity is actually going to approach 2x plus 6. And if we look at that, we're going to be going towards a positive infinity here. But so that limit does not exist really. But we can think about the graph 2x plus 6. Its right-hand end behavior goes to positive infinity. How did I get 2x plus 6 here? Because this part's going to 0, that part's going to 0, this part is 1. This is the only thing that remains that's dependent on x. 2x plus 6 is my quotient. If I did my long division, my remainder goes away there, and I have a divisor of 1 there. So is there a slant asymptote for what we were just talking about? Yes, there is. Let's prove it. I think that's what we were just talking about. So 2x, 2x squared, and 2x, subtract, 4x minus 2. This is going to be plus 4. Subtract. And there's the actual 2x plus 4 is my slant asymptote. So don't just try and do this division technique and say, oh, well, that's my slant asymptote right there. No, it's not. This is not your technique that you use to find your slant asymptote. You still use your long division to work it out. All right, that is it for this problem. And let's look at the next one here. So degree of the top and degree of the bottom are going to be the same here. I'm going to pull out a absolute value of x to the third, because remember, when I take the square root of x squared, it's going to be the absolute value of x. I do that 3 times here, and I get this or this. So, and I'm going to have 25 plus x to the negative second plus 2x to the negative sixth. Up here, I have 10x to the third minus 3x squared plus 8. Remember that the absolute value of x cubed is going to be equal to x cubed if x is greater than 0. It's going to be negative x cubed if x is less than 0. We're on this side here because x is going to positive infinity. So I'm going to make that replacement here. Plus 2x to the negative sixth. I'm going to multiply top and bottom by x to the negative third. And I'm going to get limit as x goes to infinity, 10 minus 3x to the negative first plus 8x to the negative third over square root of 25 plus x to the negative second plus 2x to the negative sixth. So that's going to give me 10 minus 0 plus 0 over the square root of 25 plus 0 plus 0 is 10 over root 25. Is 10 over 5 is 2. How many horizontal asymptotes can the graph of y equals f of x have? And most it can have 2. And we've looked specifically at the example of arctangent. So y equals arctan of x has 2 HAs. Sketch an example of a function that satisfies the following conditions. Limit as x approaches 2 of f of x is negative infinity. So it's doing the same thing from the left and the right at 2, going to negative infinity. So that's going to do this. And then limit as I go to positive infinity is infinity. Limit as I go to negative infinity is 0. Ooh, I'm not allowed to do that, I don't think. There's no such function that I'm actually going to be able to write that has a limit that doesn't exist on this side, unless this is piecewise defined, which it's going to have to be. And 0 from the right goes to positive infinity. So let's plot the given points first. So do we have any points that were given to us? Let's say f of something equals something. No. But we do have some asymptotes that were given to us. Let's see here. I think that we have some space. Yes. So let's figure out all these vertical asymptotes next. So at 2, there's a vertical asymptote. At 0, there's a vertical asymptote. And at negative infinity, I'm not sure if I'm coming at it from above or below, but there's going to be a horizontal asymptote at y equals 0. And at infinity, we're going to go to infinity somehow. All right, so we don't have any points that tell me whether I'm going to be able to cross or not. So something like this piece down here would work. And then we need something like, and they gave the example of having 1, 0 as a point. I don't think that was actually given to me, but if it was, I'd have to put that fixed point on there. And then we could maybe go through over here and have something like this. Okay. That's what I just did. Let's look at another example though. Here, this limit. limit as x goes to infinity of negative 2x to the fourth minus 6x squared plus 3x minus 9. And so we have negative and even, and we're going to positive infinity. So this is going to automatically go to negative infinity. Number 2, limit as x approaches 1 from the left, x plus 1 over x minus 1. Let's try direct substitution if we can. And we get 2 over 0. I'm not allowed to divide by 0, but that tells me that there's going to be some type of asymptote. If I'm coming at 1 from the left, this is going to be a positive number over a negative number, is going to give me a negative number. So this is going to go to negative infinity here. Use your graph if you need to say there's a vertical asymptote here, there's a horizontal asymptote here at y equals 1, and at x equals 1, and at negative 1, and at negative 1, coming at it like this, and like so, and then up here like so, and we're coming at it from the left here. It's going to give me a negative infinity. Now let's think about limit as x approaches 1 from the right of this same graph. And we have that right there is going to be a positive infinity. Let's do another example here of sketching this graph. So I think this is the same thing maybe as what we did up here. Let me make sure. Negative infinity, 0, negative infinity, infinity, infinity. It is. We just copied the same page again. So sorry about that. But you could come up with a different graph if you wanted to. Just because we made a graph that looked like this last time doesn't mean that you couldn't. For instance, this time, I'm just going to show you one of the other things that could happen with this is we have 2 negative infinity on both sides there. This is going to go to some kind of positive infinity as I go to the right. So it might just go like this, and it might go towards let's have it go like that. And that's not going to be vertical. That's just going to maybe it even goes like this. All right, this was like so. Now this one, we had it staying down here, but there's no reason it couldn't cross and then come back down like so. That happens sometimes. We'll talk about how we know that it does that with calculus later. But it is allowed to cross an HA. It's just never allowed to cross a vertical asymptote. So, all right, that is it for this video. And we'll come back next time and we will talk about continuity, which is going to be our last topic in this first unit. And then we'll come back after that and start talking about derivatives. So see you next time to talk about continuity.